So here is also an unbalanced three-way splitter. So why is this an unbalanced three-way splitter? A three-way splitter is simply two-way splitters inside. It's a two-way splitter, and one of those legs of the two-way splitter is actually split in half again to be out. So this leg would actually be the lower loss port because it's only going through one two-way splitter. These two output ports are the higher loss ports because the input signal goes through two-way splitters. So if it goes through one, each splitter is about 3.5 to 4 dB of loss. So you would have 8 dB of loss going from in to the output ports. Whereas this port here would only have 4 dB of loss for an unequal power divider.
And sometimes on a system design map, you'll see the unbalanced splitter. It'll have 3 outputs off the circle, and one will have a dot. And the dot would be the low loss leg, the 3.5 or 4 dB down leg. The other two, of course, then would be the high loss legs or the 8 legs.
And like the other passives, these are bidirectional. They get three-way split or three-way combined. Signals can come in through the output port and be combined at the input as well.
Also very important, if we're calculating the upstream path loss, not to be confused with return loss, but the upstream path loss of your 2 high loss legs would have more upstream loss. Therefore, your transmit levels would be higher on those legs.
Correct. A three-way balance splitter has a slightly different block diagram. So as you go into a device, the first component it sees is a directional coupler. So this directional coupler taps off a certain amount of signal here, then splits it 2 ways to go on each side. So this is a balanced 3-way splitter. This is typically maybe a 6 dB, 5.5 dB, 6 dB directional coupler going down here. The through loss on this directional coupler may have 2 dB of insertion loss going in this path. Then you have another 3.5 to 4 dB, so that each of the output ports has the same output power in a balanced 3-way splitter.
So this device is one of those that I would define as a combination device, right, Neil? Because it has both a directional coupler and a splitter embedded in it, which I think is going to bear a lot of resemblance to a tap, right?
Yes. And we'll be talking about taps shortly, right after this. And you can see the configuration of this directional coupler is very different than the tap, whereas the coupled port on the directional coupler is going to be in the output here. And when we show a tap in a few slides later, you'll see this block diagram being a little bit different, but it is a directional coupler and a splitter as well.
Yeah, it'll be the opposite. The through leg will go to the out, and the down leg then would go to the splitters.
Exactly. Power inserter. Power inserter is quite simple. It has the RF going in and out, and it is really just combining the AC from a AC power supply to inject AC into the network, into the main line. This is also bidirectional. There's no direction associated with a power inserter. AC and RF can go on in either directions.
Very important, though, because if you don't have power, typically you don't have a network, unless, of course, you're talking about passive optical networks, but then you don't have RF passives either. So there's that.
One of the passives is an inline equalizer. So what inline equalizers do is they compensate for hardline cable slope. Inline equalizers also pass AC. So there's an RF filter here that is a cable equalizer, and I'll go into that a little bit. And AC routes around that as well. That the AC doesn't go through the RF components, but it routes over and through that. There's no fuses associated with it because this is just a 2-port device. Power goes in, power goes out. And to explain the inline EQ equalizer, we kind of need to understand the attenuation of coax. The attenuation of coax is a function of frequency. So here's a specification of a hardline coax. As you can see, the attenuation increases per 100 feet of coax between 5 megahertz on up. So this is the curve of attenuation per 100. So if you have a very short piece of cable, let's say 5 feet, you're getting pretty much a straight line, very little attenuation. But as the length of the cable increases, if you measure the frequency response at, let's say, 50 feet, you can see there's starting to be a little down tilt to this. And this is will be more pronounced as the length of the cable gets longer and longer. And what we call this is, as the signal travels down the cable, the higher frequencies are attenuated more than lower frequencies. And this is the cable slope. And as there's more cable in the network, this is the type of slope you'll see as the signal travels down the cable.
I think it's important to note that coaxial attenuation is not perfectly linear, right? That has a little bit of shape to it.
Correct.
And we talked about shape earlier, and it is important. As we mentioned, there's a lot of cable in some of these networks with longer cascades of amplifiers and segments of trunk cable and feeder cable. It's not unusual to end up with several miles of distribution and trunk cables inside of a node. And the more cable there is, the more that shape accumulates. And so when we're talking about equalizers, it's really important to understand that there are different types of equalizers, right? There's cable equalizers, which are the inverse of that cable shape, again, not being perfectly linear in its loss to frequency relationship, versus something that's called a linear equalizer, right? Which is, as the name would suggest, linear in its relationship between frequency and loss or equalization. So what we're talking about here is cable equalization to counter the shape of loss through coaxial cables.
Correct. Well said. And here is an inline equalizer, and this is like the cable slope, so it's cable shaped. And a linear equalizer would be more of a straight line, but how cable has a slight down tilt to this. So the frequency response of the equalizer, inline equalizer, this is the filter that's inside the inline equalizer. It's equal and opposite the cable slope. So when you put the two in series together, let's say this is an 8 dB cable equalizer, so this is 8 dB length of cable, you would get a straight line. Well, ideally a straight line with a certain amount of flatness to it. So this way, cable equalizer, inline equalizer, compensates for that tilt that's shown in the cable to make it a more flat response after the cable equalizer, inline equalizer.
So let me ask you this. In some of the more modern networks, with the prevalence of conditioned passives, it seems to me that inline equalizers like these are becoming less common. Would you agree with that statement?
Yes, and inline equalizers is two ways to help equalize the network. There you got to compensate for the upstream and downstream equalization. You can do more fine tuning by equalizing within a multi-tap, or you could put an inline equalizer like you have here. They're done both ways in the network, but more and more customers are using the equalization conditioning feature of a tap to do this slope and tilt compensation.
Yeah, so that's thank you for that. And that's what I was trying to maybe point out to the listeners is in systems that were designed and built 10, 15, 20 or more years ago, inline equalizers were actually very, very common, right?
Right.
And there were even certain types of equalizers that had additional conditioning in them, not just the cable equalization. But I think the next slide will show that there's some variations in inline equalizers where in the one to the right, you could actually condition your upstream independently of the equalization of the downstream. So there are technicians may run into them where they've been in the system for quite a while. And when you remove the plate out of the coupler housing, you'll see there's places for passive plugins, maybe an equalizer, cable equalizer for the downstream, and potentially an attenuator for the upstream.
Very good. That's exactly what there's two different types, and more of the legacy equalizers that are in the field are the one on the right, the diplex versions. You can see that. And the diplex version, what is diplexer here? It's combining frequencies, like we mentioned. Well, H is the higher frequency, which is downstream. L is the lower frequency band, which is the upstream. So the upstream signals can be compensated with an attenuator, and the downstream signal has a different dB values for an equalizer that can be plugged into the equalizer slot. Typical equalizers could be 8 dB, 12 dB equalization. But the one on the left doesn't have equalizer. That is a full bandwidth equalizer. This equalizer goes all the way down from 5 all the way up to the highest frequency of operation across the whole frequency band.
So these are becoming more and more important, I think, to be identified as systems may want to upgrade their return path to start to approach symmetrical upstream and downstream speeds. Most of these, I would guess, the legacy inline equalizers that have upstream conditioning through the diplex filter feature were mostly sub-split. From years past. And so we have seen this in systems that are going through mid-split or high-split upgrades, where these devices have to be identified and removed, because any device that's past it, meaning customer premise equipment, won't be able to leverage, the additional upstream bandwidth of a mid-split or a high-split system because of the diplex filter in that device. So I think we'll talk about that in taps too, right? When we talk about
so this is a great discussion, because as people migrate subsplit, and this is the frequency response of that diplex version, there's a diplex filter here. So the subsplit has very low loss, and this could be actually adjusted with the plug-in attenuator. But since there is a diplex filter in here, as networks migrate from subsplit to mid-split to high-split to ultra-high split or whatever, or no diplex, using a full bandwidth equalizer allows us to make those network split transformations without coming back to revisit these inline EQs. So if you do have a diplex version in there, as you change these architecture in your network, you may have to find all the diplex versions of the inline EQs you have in the network and replace them.
Now, these did serve a good purpose back in the day. I promised myself I wouldn't say that, but I've been around for a while. And it's just an illustration of different design philosophies that different companies have had over the years, right? Certain companies wanted to have the largest footprint in their tap design as they could for efficiency from a power perspective. So that meant a lot of taps in cascade. And towards the end of lines through these long distribution networks, you needed to have equalization because of the amount of cable in front of it. But at your lower value taps, your transmit levels are also lower because your upstream path loss is lower. Again, attenuation being a function of frequency. So the companies that wanted to keep their transmit levels higher, because level often equals signal quality, would put in a diplexed equalizer, or some cases even taps that had the ability to increase the attenuation in the return path to keep those transmit levels high. So I think we're seeing a shift in the design philosophy of networks. So if you work in a network that was designed and built 15, 20, 30 years ago, I think these devices are a lot more prevalent with diplex filters in them versus a network that was designed and built in the last 10.
Correct. So those are the main mainline passes. We're going to go